So this segment is about solving this equation, which is the non-compounding, non-relativistic first principles formula for H. Well, it turns out there are two ways to solve this formula. The first is to just solve it, which we're going to do in a moment. The second is a little bit more sophisticated and a little bit more accurate, which is to use a process with steps back in time. And what I mean by that is that if we calculate H for a galaxy or an object that's closer to Earth, and then use that value of H to estimate the blended value of H for an object further back in time, or further where dl is at a longer distance, then when we solve for that second object, we can plug in the value of HB from the first object and then simply solve this for H1, which is a lot simpler and would lead to a series of H1s for different objects as we move further and further away from the Earth with objects that have longer and longer dLs, and for which the initial time equals 0, is further back in time. And I must say that I hope that other physicists and cosmologists do employ that stepping back process in order to calculate the values for H1 for various objects. Anyway, now on to the task at hand, which is to solve this equation. And the first thing we note is that we can't solve this equation for two distinct values of H. And so we finally have to give up the precision of keeping track of the fact that H1 and the blended H are different values. And we do that by writing the formula in this way, just using the variable H in both places. Now, in another segment called Looking Back in Time, you may have already seen, or you will see, that this value for H is actually going to be a value that's much closer to this value H1 than to the value of H at the present time. But before we move on to solving that, let me just show you how the solution is going to end. And what we're going to find is that the equation converts into this, which is a standard quadratic equation. And this can be solved using the standard quadratic equation formula, which I've written here. I've just denoted c as c prime so as not to confuse it with c, the speed of light. And from this formula we can see that the a in the quadratic equation is 1/2 dl over c. The b in the quadratic equation is 2 minus 1/2 of the redshift. And the c prime in the quadratic equation is the redshift times the speed of light. Now the fun part is that you can put this equation onto a spreadsheet if you have data for galaxies and supernova at various distances from the Earth with their redshifts, and solve it on a spreadsheet to find your own calculated values for the Hubble constant from first principles. One of the things you'll see as in solving any quadratic equation is that there'll be one solution for the positive square root and one solution for the negative square root. And you'll find that the positive square root solutions are numbers that you will easily recognize as being about half the value of h for that same object when calculated by the simple cosmological redshift formula. The values you'll find for the negative square root solution will be very large negative numbers. And I'd like to warn you not to fall into the trap of disregarding those solutions to the equation, because we've seen in physics so many times in the past that the second solution to one of these quadratic equation formulas, even though at first it looks somewhat bizarre, it ends up actually having real meaning and describing something meaningful in the real physical universe. Now let's move on to converting the non-compounding, non-relativistic formula into that quadratic equation. I'll do this pretty quickly, so it's hopefully not to bore you. We start here, bring the initial wavelength over to this side, and then multiply those out. That yields this. Then we notice that this term is some number over the speed of light squared, so this number is going to be very small. So to simplify things, we disregard this term because it's so small. So that leaves us with this part rewritten, looks like this. And then multiplying both sides by the initial wavelength, and then subtracting the initial wavelength, and then dividing, gives us this recognizable kind of formula, which is the redshift equals, and then in this case, d1 plus dl times h over c. And we still don't know what dl is, so we'll take care of that on the next page. Okay, you recall that d1 equals dl over 1 plus y from our toolkit. So we substitute that in for d1, we get this. And we bring the dl's out to the side, giving us dl times 1 over 1 plus y plus 1 times h. Then we bring the dl over to this side of the equation, and then for simplicity we put an x there, representing the wavelength times c over dl. We also expand this, multiplying by the h's, gives us that. Then we create a common denominator, 1 plus y, gives us this. Bring the 1 plus y over to this side, multiply the h in here, add the h's, gives us this equation. Expand that, gives us that equation. Subtract these out to the other side. Now we oops, I think I'm off the bottom of the page. Okay, sorry about that. So I think we were here. Subtract these, take them over to the other side. Then we just substitute in the values for y and x from up above. So 0 equals 2h, y is 1/2 dl times h times another h is h squared over c. X from up above is the wavelength times c over dl. Y is 1/2 dl over c times h minus x. Here the c's cancel, dl's cancel, so this middle term simplifies, and then we combine this middle term with the two h's over here, gives us the final middle term of 2 minus 1/2 of the wavelength times h. We had the first term here, came down 1/2 dl h squared over c, and the x is simply what it was above, minus x is minus the wavelength times c over dl. And that is the quadratic equation that I showed at the beginning of this clip. Oh, and in reviewing this, I realized I just made another little mistake at the end of my last comments, where I was pointing to these things and referring to them as the wavelength, and I meant to say, obviously, the redshift. I just misspoke when I called them the wavelength.